Hey guys, it's Chili here. Welcome back to Advanced C++ Tutorial 4 Part 2. In the last video, I taught you guys about angles, about trigonometry, and we learned that we can take any point on the positive x-axis and we can rotate it by any angle that we want. But the problem is, of course, when we're making our games, our models and our things, the points aren't always going to be on the positive x-axis. In fact, they're going to seldom be there. So if we want to be able to rotate a point that's not on this axis, we're going to need a little more math. This is useful for things like generating our star. We can start with this and generate the points of the star by rotation and then, connect the dots. But it's not going to be useful if we want to rotate our existing models. So how do we take an arbitrary point anywhere in our coordinate system and rotate it by an angle to another point? Well, I'm going to give you three derivations of this. All right, so let's call our points P and Q. Q is the point after rotation. We've got two angles here. We've got the angle that P makes with the positive x-axis, and we call that theta, and we got Q, which is the angle between P and Q. If you draw lines from the origin to Q and to P, the angle between those lines is going to be theta. That's the angle of rotation, the amount of rotation. All right, now we don't know theta, we only know phi, the angle of rotation, and our point P. So we need to calculate theta, and then you'll see why in a second. Now, we can say that sine theta is equal to py over the length of the vector p. And that's just SOHCAHTOA, right? Because y here, if this is our angle theta, this is the opposite, that's y, and here's the angle. This is just the SO of SOHCAHTOA. Because if this is our angle theta here, then this is our opposite, which is y, and this is the hypotenuse, just the length of p. So, rewriting that is we get sine theta py over the length of p. Now we can take the arcsine of both sides of this, and the arcsine of sine is just theta, is equal to the arcsine of py over hypotenuse. And now we have theta. So once we have theta, to get the total angle that this line here makes with the x-axis, that's just going to be theta plus phi. And once we have this total angle, we're home free, right? Because we've got this angle here, and we have this length here. So we can use SOHCAHTOA now to calculate the values of sine and cos for Q. So the basic idea is you're going to rotate some point from the standard position here, x equal to 1, going to rotate it by the angle phi plus theta, and then you're going to scale it by the length of Q, which is the same as the length of P, because when you rotate these guys, the length isn't going to change, right? It's going to be the same length. So you get Qx is equal to the length of P times the cos of theta plus phi, Qy is equal to the length of P sine theta plus phi. And the length of P is calculated here, theta is calculated here. There you go. It's a very simple, very naive derivation of this formula. The problem is, it is also very slow because you've got to calculate this length, which is going to require a square root, and you've got to calculate this theta, which requires arcsine, plus you've got to calculate sine and cos here. So this is a slow way to do it in terms of computational complexity. All right, now let's take a look at the derivation that pretty much everyone gets shown in a university computer graphics class. Now this one requires something called a trigonometric identity. And trig identities are just a way of rewriting trig expressions. So there's a shit ton of them. Look at this. This is the wiki page. There's a lot of them. But what we're interested in is the angle sum and difference identities. So what this is saying is that, let's take a look at this one here. The sine of two angles, A plus B, can be rewritten as sine A times cos B plus cos A times sine B. So although these two things, they look very different, in fact, they are always going to be equal. This is just another way of saying sine alpha plus beta. And I could go ahead and do a bunch of math and prove to you that these two are equivalent, but I'm not going to do that because, life's too short and ain't nobody got time for that. So we're going to use that as a little bit of smoke and mirrors to get a much nicer derivation, much faster derivation of rotation. Okay, so we got P and we've got phi. Those are the things that we know. And then there's also theta and Q. I've also given us, in this one, I've given us R. R is just the length of both P and Q because they're going to have the same length, right? So I'll just give them a single name and call it R. So we know that Px is going to be R cos theta, right? Just our unit point here and then scaled by R. And Py is going to be R sine theta, same idea. Now this angle here from the x-axis to the red line, that's just theta plus phi. So Qx is just going to be R times cos theta plus phi, and Qy is going to be R times sine theta plus phi. Now here comes the smoke and mirrors part, because we can use this identity here, cos alpha plus beta is equal to cos alpha times cos beta minus sine alpha times sine beta. Notice that this plus and minus here, it's flipped on this side. So whatever sign you have here, you've got to have the opposite sign over here. So we can expand this cos alpha plus beta into a bigger thing. So we expand this, we get this, okay? And then we can distribute R to both of these terms, and we get this. And we can do the same thing for Qy. We can expand this. So the angle sum for sine is going to be alpha plus beta is equal to sine alpha cos beta plus cos alpha sine beta. Notice that this one has the same sign. And that's going to look something like this. So now we have these two expressions here, this one and this one. You might say, Chili, you've taken something that looks a little nasty and you've made it look very nasty. What is up? Well, here comes the cool part, because let's take a look. Let's just take a look at this part here. What do we know about it? Well, R cos theta cos phi. We don't know theta yet, but we do. Let's look at here. What is this? We do know that R cos theta is equal to Px, and we do know Px directly. That's one of our inputs. So what we can do is we can substitute Px into this part of the expression. And we can do the same for Py. We can substitute Py into this part of the expression. And let's see what happens when we do that. We get Qx is equal to Px times cos phi minus Py times sine phi. And we know phi, and we know Py, and we know Px. So this just formula gives us directly Qx from our inputs. And again, the same for Qy. Let's take a look at this one here. R cos theta is equal to Px times sine phi plus R sine theta is equal to Py times cos phi. And there you go. You have got your derivation here. And this is actually a lot faster than the previous one because we don't have to calculate arc sine. You don't see any arc sine, arc cosine here. And we don't have to calculate the length. We just take our inputs. We do have to calculate cos phi and sine phi. You can't get away from trigonometry when you're doing rotation. You're going to have to do some trigonometry. But this allows us to do the rotation with the minimum trigonometry possible. It just requires a little bit of smoke and mirror in terms of this trig identity here. But if you understand the trig identity, or at least you believe it, then it's a very straightforward derivation. All right, now I'm going to show you one more derivation. This one is a Chili original. I came up with this one basically to have a derivation that's a little more intuitive, a little more tactile. You can reach out, you can feel it, you can give it a good feel, give it a good squeeze. Okay, it's getting weird now. Anyways, so let's get started. So let's start off by saying we've got two unit vectors. We call them x hat and y hat. I believe you are familiar with them. You may have met them before. So we got x hat and we got y hat. Now let's define a couple of basic functions. We're going to define our own functions here. And the functions are going to be rot phi of x hat and rot phi of y hat. So this is going to give us the point of the vector after it's been rotated by the angle phi for x hat and y hat only. Specialized, very specialized function. So you guys already can tell me what the rotation of x hat and x hat is going to be. by angle phi, right? Because this is just a point in the standard position, length of 1. You don't even need to scale it. All you do is you're going to say, well, this is going to be equal to cos phi times x hat, right? That's the x component is going to be cos phi. The y component is going to be sine phi. And the y component, we get that by multiplying by y hat. So there you go. Rotation of x hat is equal to cos phi x hat plus sine phi y hat. Now the rotation of y hat is a little more difficult because it's not in standard position. We're not used to rotating starting from this axis. But if we do a little trig, we can make it work, right? So if we're rotating a point starting here to a point here, our rotation angle is going to be phi, this guy here, which is this angle here. So now if we use SOHCAHTOA, we can figure out what the x is going to be, and we can figure out what the y is going to be. So here the x is going to be the opposite side of the angle. So we want SO for that, sine. That's sine phi times x hat. But notice that here, it's going in the negative direction. This line is moving in the negative direction, or it's positioned in the negative direction. I don't know how you say it, but anyways. So that means we got to add a little negative here. So the length of this is going to be sine phi, but that is moving in the negative direction, so we got a little negative in here. Fair enough? Okay. Now the length here, this is the adjacent side, right? And that's going to be cos phi. And that gives us the y component, and this one we can see here, that's positive, that's moving in the positive, so we don't have to do anything, we can just multiply by y hat. So here we have our formulas now for rotating x hat and y hat by phi. Alright, now let's solve the thing that we actually want to know, which is rotation of an arbitrary point P. So the rotation phi of P is equal to the rotation phi of Px times x hat plus Py times y hat. So we're just taking this vector P and we're decomposing it into its x and y components. Alright, now what I propose to you is that the rotation of phi of this is equal to rotation phi of px times x hat plus rotation phi of py times y hat. So I believe that you can take this addition outside of the rotation equation and won't change the result. So let's prove that with a little bit of diagramming here. So you've got a point P, we're going to rotate it. So we're going to rotate the vector for the point P. I don't know how much I should rotate it by. Let me just move it up here. No, we need to rotate it a little more. Maybe that much? So you can't see it. Well, let me show you here. I've rotated this by negative... you can't see it. Okay. I've rotated this by negative, 55 degrees, basically. So now I'm going to rotate the individual components of y and x by 55 degrees, and we're going to add them together and see if they add up to the same thing. And we can see here that indeed they do add up to the same thing. So if you rotate the components individually and then add them together, that's the same as rotating the whole thing at once. So we can rewrite this as this right here. All right, let's now do one more little reworking here. We're going to pull the px and the py outside of the rotation equation. So what we're saying here is that rotating the scaled component x and y is the same as rotating x and y and then scaling it after the rotation. And I think intuitively you can see how that is true. Let's take this vector here and we're going to scale it so that its length is now 3, and then we're going to rotate it by some angle like this. That would be equivalent to rotating the original vector first and then scaling it by the same amount. So we can see that the order of scaling and rotation doesn't matter. You get the same result. And so these two expressions here are equivalent. And now I think you can see where I'm heading with this, because we know rotation phi of just x hat, and we know rotation phi of y hat. That's just these guys up here. So all we got to do then is substitute. So if we substitute this into here, and then we distribute the px to both parts of the sums here, what we get is, so we get px cos phi x hat plus px sine phi y hat minus py sine phi x hat plus py cos phi y hat. And if we collect the x hats and the y hats together, and factor out. We get for the x hat, for the x component, it's px times cos phi minus py times sine phi. And for the y component, we get px times sine phi plus py times cos phi. And does this look familiar to you? Because it's just exactly what we had from the previous derivation. X cos phi minus y sine phi for the x component. It's the same result. It's just a different way of looking at it. So I think this derivation, personally, I believe it's a little more intuitive because you're working with the vectors and you're working through the steps all by yourself. Whereas this derivation has a lot of smoke and mirrors inherent in the trigonometric identity that we use, the angle sum theorem. But it's all the same stuff in the end, and what we end up with is this canonical form, which is going to drive all of the rotations in all of our games. All right, now let's fulfill the promise, the prophecy, the covenant of Advanced 3 solution video. That is, well, you remember what happened in Advanced 3, hopefully. We had to fix a little problem with the rebounding where it would get stuck in the line. And the way we fixed it, well, let me show you. Quick little refresher here. We fixed it by doing a bunch of this math bullshit. And I told you that it would be easier to fix with rotation. So how would we do that? So we got some points P0 and P1. They represent the start and the end of the plank. And we can get a vector along the plank with W by subtracting them. Now what we want to do is we want to get a vector n, let's write that right here, n, which is 90 degrees or pi over 2 rotated relative to W. So we could do that math bullshit that we did before with the, the distance of a point to a line formula bullshit here to get this vector, or we could simply rotate W. Here's the formula for rotation, and so we need to calculate the cos and the sine of phi, which is going to be pi over 2. Actually, it's going to be negative pi over 2 for our rotation. So you pull out your calculator and stop right there. You don't need a goddamn calculator to calculate this. Have you forgotten your training? Sine and cos, they relate to the unit circle. So pi over 2, negative pi over 2, that's going to be these points here on the unit circle. Do you need a calculator to figure this out? I sure as hell hope not. It's going to be 0, 1 for the pi over 2 rotation, and it's going to be 0, negative 1 for the negative pi over 2 rotation. So you substitute those guys into here. That is to say, you make these substitutions here of negative 1 and 0, and you simplify. What you're going to get is nx is equal to wy, right? Because negative 1 here and this negative 1, this negative cancel out. And so this becomes just positive py, which in our case is going to be w. We're rotating w to find n, right? So nx is just equal to wy, and ny is equal to, well, you put a 0 here, this cancels out. This one also canceled out, by the way. So it's going to be negative x, which is negative wx. So there you go. Rotation by pi over 2 or negative pi over 2 just boils down to this super dirt simple process. And since rotation by 90 degrees for you plebs is such a common thing, I often actually put this operation in my Vec2 classes or Vec3 as a separate, well, not Vec3, but Vec2 usually as a separate function clockwise 90 and counterclockwise 90, because it's very common and it's also very fast for the special case of 90 degrees. But we're not gonna do that right now. We're just gonna use this directly to solve our problem. So here it is. Here's all the work that we did in order to get that plank normal. Let's delete it all because we don't need it. You're gonna be so amused by how simple it is. So let's do const auto plank vector get surface vector. So we'll get a vector in that direction, and then we're going to do const auto plank normal. I say quote unquote normal because we're not actually going to normalize it, and that's just equal to, well, here x is equal to y is equal to negative x. So we got plank vector dot y and plank vector dot x negative, and we'll just put a little semicolon on the end of there, and there you go. We've got our plank normal. Suppose we've got to tell the compiler that it's a Vec2. Now it's sort of happy, but not really. Oh, it needs the plank points, and it needs the ball position. I got to do everything for you. All right, now are you happy? No, we still got red. What is it? All right. So I reinstalled Visual Studio, and when you do that, you're going to run into the problem where your installed SDK version does not match the solution SDK version. The solution, very simple, change your Windows SDK version to the one that you actually have on your machine. You apply that, and the red goes away. You build it, and when you run it, you got your balls. They are rebounding off the plank. If you swing into them, no problem. So, same effect, much less code, also going to be faster, and a lot simpler to understand. Yeah, a little comment here because this isn't super clear. And there you go. Little commit and you are ready to roll. So that's how understanding the beauty of rotation in trigonometry can really help out your coding. I just added this in a little bit in post because I realized that I forgot it and videos were short enough to add this in here. So a little bit of a bonus, edit it in post. Now back to your regularly scheduled programming. Get it? Programming? Because it's a tutorial about C, yeah. But that's going to about do it for this video. Stay tuned for the next one, part 3, where we are actually going to do some programming in this programming tutorial. We're going to implement the rotation formula for our vectors, and we're going to do a simple rotation test, and then we are going to put it into our pipeline. And also look at some ways that we can optimize it. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more advanced C++.